So anyway, so I think a couple of people have asked me, how do you want the test turn in? And that's obviously a good, reasonable question. I should have mentioned it there. So what my thought is the test has two parts, right? So the written part and then the CAD part. And I'm guessing what we could do is written or typed or however you're putting it together or typed. All of this could be, it's up to you. Either you can give me a hard copy if you prefer, or you can zip it along with the rest of the work. You can just give me a PDF of it as well, scanned copy, right? It's fine. Again, like I asked that please name your files by your last name and kind of give me an idea what it is, like theory or something. And then if it's a .doc or .pdf, that kind of thing. So I'll know that that's what you have talked about. This one, like you did last time, is fine. So I'm assuming all this will come through Vault, like you did before, right? And on this, I would say, only request here is if you can just zip or compress the file into one folder, right? Happy to receive 20 files, but it can be easy to miss half of them, right? Especially on a football Sunday or something, so Saturday. So this would be the goal. And as far as the CAD itself, just talking to Stephen here, so maybe, all your part drawings, part files, not part drawings, but part files, your assembly or sub-assembly files, right? Assembly files. Along with this, it might help me to have a Word file with how you approached it. What I mean by that is, if you have, because you made a lot of assumptions in the developing the product, right? So I would like to know what those assumptions are, and what have you done to personalize the design, right? You can say, okay, I made the base broader, I added these lips in this direction for this reason. I made this connection bracket because it seemed to work in a certain fashion. I developed this bearing to work the telescoping action of the handle. I had end caps on the handles for grip, for example. So anything that you have done, you had the brakes were a certain angle because that's how, in terms of safety or other considerations. So what's the thought process that has gone into just cannot be gathered by just looking at the drawing. If you can explain that a little bit in a Word file. And if something did work, you can say that also this part didn't work for this reason, or it seems out of proportion or something. So in terms of any proportion consideration, if something was out of whack in terms of fitment, all of that can be explained as well. And then the exploded view, like I said, either you can make a separate file for it, or integrate that into a Word document or a separate file if you have to show that. Like I said last time, have flexibility when you are doing this. So each person's product, I'm assuming, will look a little different, and it will be for a reason, right? If you're a designer, you're going to come up with same function but different ways to come to that product. So that would be a good. And what I might do is ask each of you to spend maybe 5 minutes in a class and kind of go over what you've done. Not necessarily go through each step, but in general terms, we can put up your model and you can explain to the class, this is how I personalize my product, and this is why I did this. And just so that it's more of an interactive design discussion where the team does, so at least we'll have that experience more or less. So that's kind of what I'm thinking.
And as far as for little things like bolts, nuts, and washers, do you want us to to make every single bolt file, or could we import something from McMaster?
Yeah, absolutely. I was saying that any general common fitments you can import, just reference them.
Inventor has
Library.
a library of
Yeah.
bolts.
That would be great,
Okay.
just to reference them.
Yeah, you mentioned orthographic drawings of each part as well in the test. Do those need to have like full sets of dimensions?
You should have enough dimensions to make the judgment on don't call out every single dimension.
But enough to actually fabricate.
Correct. If somebody, the machinist looked at it, he should know, he or she, that this is your broad idea. So, again, the whole purpose of the product is to communicate the design, interact with people who would either fabricate it or interpret it or make management decisions on it. Sometimes if you're making thousands of these, there may be certain management steps involved in it. So it's kind of to communicate across the board, right? Across all those constituents. That's the idea. So as you go to the top, higher and higher, their attention span becomes less and less. So you should be able to convey it in elevator speech. As you go lower and lower, you're able to give as much detail. The same product, who is being pitched to, makes very different audience. Right? So you have to kind of be ready for that, I guess. Yeah.
Yeah, the only other thing I got is the motion bit there. How do you want that presented? I'm having trouble actually finding how to do that.
Okay, so I should probably go that. Okay. So save that thought and how do you want to present it, right?
Maybe there's a presentation file where you can like.
Yeah, you can do an animation file in which you can set it as a AVI or a MPG kind of. That way you can play it and
You
it
can make small videos with it.
Right.
You can do a presentation, open a new presentation,
Yeah.
open up your file, you do that, and then you time step it. You use the time slider bar at the base, and then you can work through how the snapshots look through time.
I got you.
And rearrange them on
Like a
top.
movie file almost,
Yeah.
right?
Yeah. Okay.
But it requires going through and actually doing the tweaking, disassembling,
Right.
moving, and then snapshotting it.
Yeah. Okay. That makes sense. I know how to do that.
Okay. So I think we'll say 19th, then we said is the date, right? Next Thursday, today. I didn't see any rush of files coming in this morning or afternoon, so I'm assuming.
You say that again? The 19th. Oh, let's do the 19th?
Well, I
thought it was due today.
yeah, it was actually, and that's what I said last class. If you want to take the Thursday, just to do an extra. So.
Turn it in today if you want.
Never heard anybody complain giving extra 2 days, right?
So, for the comment for the which file, where do you want me to put it? In the individual Word file for that, or?
Yeah, your narrative file could be in Word. It can be converted to PDF if you care to, right? But it can be zipped along with the.
Oh, okay.
rest.
Okay, just find some the text file and just write a comment on it and package with this one. Okay.
Yeah, kind of more of interpretation, your thoughts, right? It should be a reflective work as well, like certain things. Sometimes the work may not be 100% complete, but at least you should be able to say, okay, this is where I'm heading with this, so here's my approach to this, like that. Okay, so this is about test one, that's good. Now, what I'm thinking is because of the time span and where we are in the timeline, the work that are associated with the problems and the CES Granta work, right, which is coming very soon. I will start giving this as modules, meaning the work I'll assign will all count towards test 2. So we'll not have homework and then we'll have the test because it gets too much complicated if I do that. So what I'll do is I'll assign maybe part 1 of test 2, part 2 of test 2, and part 3 of test 2. And that kind of can be counted as homework itself, but the work you do will go towards that test. So we can have different submission dates for those, but then all that collectively will go towards test 2. So I'll start giving, I didn't want to bombard it this week since you're working on test 1, but I will pass this out by within this week, that is week of the 16th. And we can say one module is due by, and we'll set a date for that. So hopefully all of this will be completed within a month. So by November 15th, we'll have finished test 2. And you'll at least have had experience of everything we have done with this. So, also, like I told you last class, please think of your product that you are going to work. So this product will be presented to the class, the CAD work for it, the design work in terms of math, I guess, and then the CES work related to that, the FEA related to that, any mold and tool design related to that. All of this will become the package for the product, right? And this will be end of semester deliverable. So, but this will be what you present to the class, you put a formal report. So this becomes like an extended homework in itself, right? But it will be in modules based on what your product is. Yeah, so sorry, this is a lot of work already in progress and coming through. But any questions? Does that make sense? Well, to me it does, so let's continue. Today I will advance the discussion from last class. So you recall we have started with the using the case studies, right? And first I gave you the approach to translation, and then we saw that from translation, once you set that up, you do screening, of course, right? Based on the screening in terms of reducing this, narrowing down the choices, if you will. And then from screening, you're doing the ranking, right? Ranking where you put the, incorporated the material indices. And last time, we saw, at least for the mechanical systems, we worked this in terms of tie rods, and we worked in terms of beams and plates, right? The kind of panels. We did this approach, and we saw that for certain cases, you can very nicely use this for further down selecting yourself. And then this will result in documentation once you finalize your designs based on this. And documentation can include both structured and unstructured information, right? What I mean by that is you saw when you just have an idea what it is, when you double click on that field, you can get a whole new world about that material and what it does, right? So this is the sequence more or less we will be following. So I gave you a few, I think the last time we took a case of a ore used in rowing or canoeing application, and we went through understanding the translation. From this, we saw the narrowing down of plotting the modulus versus density, I believe, and from that we down selected the specific materials, and we ranked it to, although there are 4 or 5 things would work for that, we saw that there was a brittle failure if you used a ceramic, so we discounted that and came down to 2 choices, being wood and CFRP carbon fiber composites. And then we saw that prices are going to, we didn't do any costing on that yet, but cost will become a decision factor in some cases. In some cases, the performance becomes the decision factor, cost being secondary. Like if you're doing performance sports like Olympics or high-end use of that. If it's a day-to-day common use, then maybe wood would be your choice, like that. So there are about 25-30 case studies one could get into, but again, I don't want to spend all the time just repeating that, but today I'll spend at least 2 more and then go into how integrating process now. We have, in this, all this, we have not yet talked about process, right, or manufacturing techniques. We have talked mostly on the performance side of it. So this application is an interesting one. It's around very large telescopic mirrors. So so these are the mirrors that you see out on the highways, or very large observatories. People who go up the mountains to do very deep stars and deep space exploration. We're talking about that kind of application. So it's very niche. So obviously telescopes track the positions of different things across the sky, and there are people who are very specialized in knowing what to look for, and they make a career out of that, obviously. Usually these are single rigid mirrors, and that's one of the aspect of it, that they are rigid mirrors. To date, the largest telescope like this exists in Russia. Seems like Russia has a hand in everything these days, so that is part of that, right? So this one is in Mount, what do you call it, let me say this right, Vodrica. Vodka is all I know, but and then it is near a place called on the Caucasus Mountains, this place called Zelen Chukskaya in the Caucasus Mountains. I'm just giving you some historical context when you're talking about it. Just makes it more interesting, I think. This particular telescope happens to be 6 meter in diameter. That's huge, right? 6 meters in diameter. So it is. So this is what I'm calling it general attributes, right? And 6 meters is 236 inches in diameter. So it's huge, right? And it is about 1 meter thick. So it has 1 meter thick, about this thick, and 6 meters in diameter. Why should it be that thick, you think? Rigidity. Absolutely important, rigidity, because telescope is all about high precision, right? Even the micron level change or sub-micron level change can change your focus and everything. That's why it is so thick. It weighs 70 tons. Very heavy, obviously, 70 tons in weight. To put that into context, MRAP or M1 Abrams tank that the Army uses weighs 80 tons, right? So it's about the weight of a tank in that context. And it costs about $300 million, so it's no room for machining errors there. It turns out that the mirror of this is only about 5% of the cost. So the mirror is not very expensive, it's the rest of it. The rest of the 95% is in the precision mechanism, the controls, the mounts, and everything costs that $300 million actually, right? So that is thought was interesting. So the key thing is the mechanism has to be very stiff here, very high stiffness because of the precision, and you cannot disturb the wavelength of the light, because all that results in erroneous reading. So there are a lot of strict requirements for something like this. So what is also interesting is that this the 70 tons, it's only 30 nanometers is the coating, the mirror coating. So this weight of this is only about, I'm sorry, it's 100 nanometers. So the weight of this is only about 30 grams. So 30 grams is the only mirror for a 70-ton part, right? Because it's all, the rest of it is the supporting structure. So that's, you can conceptualize it like something like this, very thin coating is the mirror coating. So it's a lot of interesting facts here. So historically, these mirrors were produced with the base being speculum. Speculum is a metal which is like steel in those days. So the density of this is about same as steel, is 8,000 kg per meter cube. Steel is about 7.8 to 8 grams per cc, so it is about 8 grams per cc. So then they switched to glass because it was equally rigid, and the glass density was only 2,300 kg per meter cube. So there was a lot of weight changes going from, otherwise it would have been even more heavier than the 17 tons that it is, right? So, so this kind of setting up, any example I'll give you, I'll just kind of think of setting up the problem there, right? And so we can take out some dark pens here. So we're talking about the mirror like that. We're just going to approximate it as a disc, essentially, on a support, right? It's like a big plate on a big support, essentially. So it's a circular disc approximation. Generally, this is a concave because it focuses to a certain focal point, supports for getting the right refractive conditions here. So obviously they want it to be lighter, they want it to be cheaper. Those would be your conditions. So let's write down, like we did for the other cases, what would be a translation here. So translation, the function has to be what? Function is that it should be a precision mirror, because it has to have very high accuracy, right? So that is one of the conditions. Obviously the constraints would be that you would work with a certain radius r specified. So this happens to be a geometry constraint, right? Also there is a certain thing like it must not distort more than a certain amount delta of its self weight. So the distortion here, you don't even need any extra force, right? Just the weight of the structure alone is sufficient to distort it. So self weight is critical in this application. Of course, it should have high dimensional stability, like we see. And also it should have no creep and a very low CTE. Because in Russia, you're going to see there is winter and temperature changes. So the objectives in this case would be to what? Minimize mass and minimize cost, right? You want to minimize both as such. And what would be your free variables? Would be your thickness and choice of material. So you have a couple of options there. So in this, like we have done in previous cases, I'll just lay down the philosophy, I guess. So this being a disk here, we are looking at mass. Now therefore the mass in terms of volume should be pi r squared T, right, times rho, because it's area times thickness. Typically we take Poisson's ratio as 0.3 in this case, but that doesn't appear in this term anyway. Then again, like I said, based on the geometry, you have to look up the appendices for the cross-sectional properties for these.
Is it possible for you to use a darker marker? It's kind of hard to.
Oh, I'm sorry, okay. Let's go to black then, you know. So Jared, you see, I'm taking it out of the new box, but still it is like that. But tell me again if this is worse or better. So based on this information here, delta is it's of the form 3 over 4 pi because of a disk geometry. Weight being mg, radius of the disk r squared divided by et cubed. So remember, in case of the beams we did the EI, flex rigidity and so on. So it's similar equation considering this particular geometry. This comes from essentially for specific geometries, so you can look those up, you don't have to derive it every time. So both these guys have t, and as you see, t is the free variable, right? And you can eliminate the t, just like we did in the other cases, right? So if you did that, t comes out to be m over pi r squared rho from the first equation here, and t from the second equation comes out to be 3g divided by 4 delta, right, to the 1/2 times 4 pi r to the fourth, and rho over e to the 1/3, and this is to the power 3 by 2. Basically you are solving this equation here. So from all this you are focused on this index here, which is e to the 1/3 by rho. You have seen this before for a plate. This is your material index that you are trying to maximize. You want to maximize this for the plate. And then there are other attributes, of course, that are more qualitative in nature, right? So, is that better, Jared, or still yes? Okay, thanks. So the other thing here is, since creep is the other thing, you can think of like the melting point should be greater than or equal to 500 degrees C. So therefore it is very dimensionally stable, avoid creep. That's why glass is very stable for that kind of application. The other condition is it should have zero moisture take up, because you don't want the mirror catching moisture, right? So that is the other requirement. So I want to get back to the software, but I think after this point I would invite you to plot the modulus versus density in the bubble chart like we have seen for a slope of this is slope of 3, and look at what conditions would appear. So you're looking on this side of the curve because you're trying to maximize these things. So you'll see in this that glass comes to be somewhere here. So it is what is currently used. You will also see that the carbon fiber reinforced plastic comes to be there. You will also see that there are some very stiff foams that appear out here, which have really not been used in this application, but they are a good choice actually. So here again, this is the current state of the art. based on, you can get higher modulus at slightly higher density. Actually, this may be just overlapping this, because here we are talking about 2300. CFRP can range between 1.5 to 2.1, depending on how much percent of polymer or what grade of polymer you use in it. But certainly these are much, much lighter, right, stiff foams, which also suggests that the backing of these mirrors could be made out of very stiff foams. But where may be the challenge, you think?
Moisture takeout.
Moisture take-up and also the creep requirement. There could be certain types of foam, but then they may have to be more thicker, or they would have to be sealed in some way. So going back to your question, Stephen, you raised in some previous class about the adhesive and paste, and this was more of the microchip we were talking about, right? So those kind of innovations get captured when you do your documentation and postscript of these understandings, right? So you first get your basic choices, and from there, if you do anything more innovative around it, you have to capture that in. So this may not be a do-all and end-all. This is more of a very, I would say, strong indication of where you need to go. And after that, you may have still a lot more you can do from that solution. So you could, don't take this as like your final step, is what I'm trying to say. There's a nice chart that can be then put in the terms of postscript, like ranking. So here, if you look at a material saying steel or the speculum, glass fiber, all these are things which pass that condition. Aluminum alloys, glass as this monolithic glass, CFRP, and foamed polystyrene, which is the foam that I've been talking about, rigid foam. So in this case, if you look at the material indices for E equal to 1/3 over rho, this comes out to be 0.74, 1.5, 1.6, 1.7, 3.0, and 4.5. Now what is the goal in material indices to be? As high as you can, right? You want to maximize the material index. So this is very high, this is very high. So that's why it turns out surprisingly that foamed polystyrene, because of its low density, it gives you a much higher value for E. So that is a good candidate actually. So based on those calculations, you can calculate the actual mass that this is going to be. Steel is about 73.6 for this case here. Glass fiber is 25.5. This is 23.1. Glass by itself is 21.6. So the 70 ton I told you, sorry, was for a steel backing, not for the glass backing. CFRP turns out to be 9, and the foamed version is only 5. Okay, so this is, we are talking in terms of tons, and this is for a 5.1 meter diameter mirror. So now you can immediately start quantifying your choices, right, based on the chart, and from that you can now start eliminating the ones that you think will definitely not work, but these are very strong candidates which would be fine. So you can now put comments like, this is original design, it is very heavy, for example. So these are qualitative things that you need to capture. What about GFRP? GFRP is not very dimensionally stable. It works, but it may not give you the right dimension. And they say that this is okay for radio telescopes. And I'm no expert at telescope, but I believe the radio telescopes have longer wavelengths, typically. And when the wavelengths are longer, they are more forgiving in this case. In this optical mirror telescopes, you've got to have extremely short wavelengths, so the precision becomes even more critical. So, but GFRP could well be used if the application is slightly different. Aluminum alloys is an option, but it's heavier than glass. Glass is a good choice here. For example, that is what is used. And future ones, of course, you can get very low density and very high performance from these. And this would be more of a research material, still not fully proven, but the chart seems to suggest that more R&D could be done for applying that. If this works successfully, then this could become the next generation material, because it's going to go from 70 to 26 down to 5. So it is huge savings in that case. So we looked at one application on the very common use. This is more of a very special use. The other two, I'll just lay down the case for you, and I'd like you to complete it in terms of review it, complete it, that kind of things.
Should we also consider the reflectivity for the visible wavelength in this case, or all these cases are almost similar reflectivity?
The coating is what,
Yeah.
Oh, yeah.
and the coating is very small.
Yeah.
It's a very thin coating, right? But yeah, I guess you should certainly plot density versus reflectivity, refractive index, all the optical characteristics similarly. I've just shown you one cross plot of modulus versus density, right? But the application would require you to look at other parameters as well. So you can selectively down select, right? And then once you have those, you can just pick those materials of down select and then plot the other factors against it. So just we are looking at one example for each case. But that may not give you all the answers just from one cross plot. So, yeah. This one is around pressure vessels, safe pressure vessels. Examples, of course, include CNG tanks, right? Compressed gas tanks, hydrogen storage. It could be tanks that carry oil and gas, chemicals, weapons, propellants. I mean, a lot of applications for such things. Right? Of course, one of the most common mechanical application is boilers, steam boilers, etc. That all these are examples of pressure vessels, correct? You can just say pressure cooker is a pressure vessel. So it could be any of those right here. So, like I said, pressure vessels, I forgot of you. Aerosols, certainly you wear a deodorant or a shaving cream, you're working out of a pressure vessel. Of course, the safety levels are much relaxed there compared to more stringent ones, as you can all imagine. Big boilers. So this problem is more related to that. So some of these, or all of these, some of the issues come about is they can suddenly burst. That is a common thing. Or they can gradually, what? Yield and leak. Right? You rather have them gradually yield and leak than burst. Right? So when you design for this, you want the crack to grow thicker than the thickness, and then slowly allow the pressure to be diffused, as opposed to have uncontrolled growth of the crack and then suddenly cause burst. The safer option is to allow it to leak. So that's done in this particular case. Therefore, it's very important to design it on the basis of fracture toughness. Pressure vessels always have to take into account that there is some pre-existing flaw in the wall, because then you are doing a safe design, because you're allowing that crack or flaw to grow. So if you consider, this is a common mechanics, you might have done this when you did mechanics of materials or theory of elasticity and so on, right? Basically look at a pressure vessel as a cross section like this. It has a radius of R. It has a wall thickness of T, correct? That is what it is. And generally when you think of pressure vessels, and if they are not made out of, or rather if they are made out of steel or isotropic material, then it's not an issue because you are just having similar properties on all sides, correct? But if the pressure vessel is wound, like if it's a composite vessel with fibers that are winding in a helical fashion like so, right? Or you may have fibers that are wound in the hoop direction, or you may have fibers that are going in the longitudinal direction, right? So your pressure could be sigma hoop, sigma longitudinal, right? Or sigma helical in terms of a certain orientation or shear. So those things become a lot more specific when the material is not isotropic or anisotropic material. When you're looking at just steel, most of the equations you're looking at is steel where all the material is homogeneous throughout the structure. So in this particular case, I'm just assuming the latter, meaning it is isotropic. So here then this stress is given by PR over 2T in terms of the wall thickness. So if you look at the typical cross section here, you can imagine there's a crack, and that crack is, like I said, crack length in fracture mechanics is typically called out as 2A or 2AC, meaning critical crack length. So right at that point the crack will grow basically, right? So here we are talking about the hoop stress in the wall, and because it's tension, it's going to open the crack and propagate the crack actually. So that's our assumption here. So this is a stress in a thin wall pressure vessel, right? So that is what you're looking at here. So obviously when you think of the translations in this applications, you have to worry about what is the function here. The function is obviously to serve as a pressure vessel and safely hold pressure, correct? Sometimes the function is obvious, but it's good for you to ask yourself that question and write it down. The constraint is that the radius is specified for this case. The objective, of course, is that you should provide high safety depending on the application. Like even an aircraft fuselage is a pressure vessel, right? Basically it's pressurized chamber, or autoclave is a pressure vessel. So you have to see what is the safety using the yield before break. Criterion, you need to know, is it going to yield before it breaks? Also you need to have safety using leaks before break. Like in a pressure cooker, you put a valve right in the valve, when the pressure exceeds, the valve will open, release the steam, and that makes it safe. That's kind of what the idea of the leak is. You're allowing the controlled leak so that it will diffuse the situation. The free variable here, of course, you can think of thickness as a free variable and also the material choice. So, but these are some of the things you be worried about. So this I won't go through the whole thing, but I'll just list a few more steps. So we know that the pressure applied must be less than reaching the one that causes ultimate failure using factor of safety. It's common in this to a factor of safety of 2, 2.53, depending on the criticality, right? Also, you know that the stress considering boundary conditions and the fracture toughness, and we discussed this when we went through the parameters earlier, is given by square root of pi AC, because sigma is equal to k divided by pi AC, right? We saw that as the case. So the K1C was the plane strain, fracture toughness. AC was representing the crack length. And C was a constant based on a boundary condition. So because we are treating this as a pre-existing crack. So if you plug this into the safety equation here, you can see that P must be less than or equal to 2T divided by R, which is that equation which I just wrote. PR sigma is equal to PR divided by 2T. So I'm saying P is equal to 2T sigma divided by R. So 2T divided by R times sigma, which is this equation right here. So in terms of this, it would be KIC divided by square root of pi AC, assuming C is equal to 1. So obviously, as a material index in this particular case, your goal is to maximize the fracture toughness, correct? You want K1C to be as high as possible, because that way you are getting to the fact that it's going to be a lot more damage resistant or damage containing. This equation can also be written in terms of crack length, AC, as being equal to C squared KIC divided by sigma y. I'm sorry, this equation here. So y happens to be the yield stress. So you can determine the critical crack length if you know what? If you know the yield stress, if you know what kind of fracture toughness you're getting, and what is the boundary conditions here. So is this an edge crack? Is it a center crack? You know, like that. That's what helps in calculating the value for C. So for the most common things, you consider this a center crack equal from both sides, but that is not always the case. You're going to have maybe a double edge crack on both sides. You may have a crack here and a crack here. Then the C will change according to that. So that is, but we are not going into that detail here. So with this background information, what you need to do then is, I would suggest you look at K1C fracture toughness as a function, right, of the density, as a function of the other factors that would be related in this work, to come up with a material that would be high in K1C, because that's what your goal is, right? And then apply that to check if a certain crack length is met or not. So you're looking for the largest value. Maybe you can plot sigma versus K1C, right? And then look at this index in terms of maximizing the index on this side to see which materials would satisfy that application. So I will do one more, and then I think, I believe we have enough background for everybody to try a few on their own. And then that's what I'll do, is this will become part of test 2 as one module of test 2. So we saw plotting strength versus modulus, stiffness versus density, strength versus density, fracture toughness versus strength. This particular one relates to energy absorption. So energy absorption again is an application, like I said, in impact. It could be in terms of stored energy, right? as you know, energy could be in different forms, right? Which is particularly in this case we are focused on kinetic energy and potential energy, right? Energy due to height, this is due to stored energy. All this falls under potential energy. Of course, the kinetic energy would be more from energy due to moving objects like velocity, high-speed bullets, and cars running at high energy and so on. But right now we are focused on one type of energy, which is the stored energy in springs. So this would be material for springs, which is the application that we are concerned here. And as you know, springs come in different flavors, right? Springs come as tension springs, like where you're just pulling, right, and then storing energy in tension. There are also springs like in your trucks and machine foundation, earthquake resistant buildings and so on, where the springs are in compression springs. So there's a limiting deflection. When these things close off, the spring has failed, right? In this thing, when a certain delta exceeds, the spring has failed. It doesn't have to fail as in fracture. When it exceeds that deflection, it is failed actually. Then you also have springs which are like leaved like this. These are called as leaf springs. So leaf springs, compression springs, tension springs, and then never mess with the garage door because of the coil springs, right? So these are coil springs. There are also springs like in the shape of torsion bars, where a certain amount of energy is imparted just by torsion and saved like that. Typically in your watches, that is how it is. It's essentially torsion springs. So these are all the forms in which energy gets stored, right, in the springs. And therefore, you have to figure out what materials would be used for some of these things. So when you do these calculations, you always have to look at stress strain behavior, right? And then usually you're looking only at the elastic portion of the response, right? So it is this is a triangle. So basically, it is the energy here is 1/2 sigma epsilon, right? Which is the area under the triangle. Is the energy stored. So then, if you think of this, then is equal to 1/2 times sigma. Epsilon is nothing but sigma over E, correct? E epsilon. So you can say that energy stored therefore is 1/2 sigma squared over E. So this is the parameter again that you are trying to work with, is the energy stored in the spring. So now remember that this is 1/2 sigma squared. E is very typical of a fish scale spring, where you put your fish here and then just load it and measure the. So this is tension spring. That's what these curves are generated. Now you notice that if you go to leaf spring or if you go to coil springs, these relationships have to be adjusted because the same amount of energy is not stored in a coil spring because of the center has a neutral axis effect. There is loss of energy between the leaves. So typically this, for leaf springs, it's common to have the energy values as approximately 1/3 sigma squared over E. Okay? If you go to a torsion spring, even less, you will see that the conversion is only about 1/4 sigma squared over E. So the storage values change from one to the other based on what type of spring it is. Nevertheless, for your purposes, it is you can see that this parameter, sigma squared over E, appears in all the cases, which means when you look at an index, this would be an important index for you to think about, is the energy of sigma squared over E. So this is based on volume of the part, etc. But we have not yet worried about changing the, looking at the weight of the spring, right? There is no mass term or density term on there. So when you want the minimum mass spring for the maximum what? Energy absorption, right? You have to now consider that this factor sigma squared has to be looked at in terms of versus rho E, right? So the energy is a function of density. So this is now considering the weight also into account. So you would look at these factors therefore in that case. So elastic energy per unit volume, like I said, elastic energy per unit volume is given by W sub V as 1/2 sigma squared over E, which is what I just said all along here. So if sigma becomes greater than sigma Y, that means you're no longer in the elastic region, correct? You're going to get plastic damage of the spring. And you know in springs like rubber band, it happens after a while. The rubber band stretches and it doesn't return to its original position. Same idea. However, if sigma is less than sigma Y, it is within constraint. So your goal, of course, is to give the corresponding safety factors and so on. So this is for a general elastic energy. When you want to look at the elastic energy density of a spring, the entire range, then all you do is replace sigma with what? Sigma F, failure stress. So you know that, completely stretch it out to failure and get that. Therefore, then it becomes called as elastic energy density. So in this particular case, then I would urge you to draw the modulus versus strength curve, like you did fracture toughness versus strength. And again, because this is sigma f squared by E, you have to look for an index with slope of equal to 2, correct? The index line of slope equal to 2, wherever that lies in the scheme of things. And then, whether if you're maximizing this, which is what you are, you're looking for material choices up in this range and see what those are for a given spring. So that is what it would be. And the options that you come across are things like titanium alloys. You may come across, again, composites here. You may come across spring steel. You may come across nylon, rubber. All of these are spring options. Then what becomes your choice is you have to look for a function and see a certain temperature range, a certain creep range, a certain, those become more looked at after you come up with the basic choice. So I think I'll close on this case study. I have several more, of course, but I would like you to absorb this information on your own, finish the unfinished business here, and then I'll be putting out at least 2 or 3 case studies for you to integrate as part of your submission towards test 2 then, and work this aspect out. Okay, now I'd like to move on then to the processing, which we have not, we have kind of done a little bit when we did sheet metal and we talked about bulk metals and forming. I covered it briefly there, but here we are tying all of this to the processing information. Because I have not yet said how the spring will be made, or how is the spring, is it assembled, or is it joined, is it shaped, is it bonded, is it additively manufactured? All of that makes a difference, right, in this case. So when you look at process information, there could be sorry. So just to recap here, we have so far then covered all this thing around material index, going from translations, and we have focused on what we have not done is looked at shape or geometry. I mean shape meaning what is the ideal shape, we have not looked at that, and we have not looked at what processes it is. So now we are migrating from here to the next step, which is process. And process is another name for manufacturing, right, in this case. So now that you all have some idea of the material options between polymers and the various materials, again let's list them. Here we have polymers, we have metals, then we have composites, we have ceramics, right, and we have what? Foams. In the context of grant, all of these things is what you come across, right? In ceramics, of course, they further go into technical ceramics and non-technical ceramics and so on. But you could go crazy with this chart alone, but let's look at just one aspect of this. I'm just looking at metals as an example here. And we have discussed this before, I'm just going to recap that. So if you look at metals in the general context, you have metals which are bulk formed metals, right? Metals which are sheet metals, and metals which are cast, right? You have these different options. Now within bulk forming, we saw there are a whole range of options being what? Forging, we talked about that in the class. We talked about rolling in the class, right? Extrusion in the class, as well as drawing, correct? So all these are options of bulk processes in this case. When you look at sheet metal, you saw that based on the aspect ratio, they are very much a different family. Although they are within that, they are very different family. When you look at casting, again you have a whole bunch of options there. You can think of sand casting, right? You can look at die casting, for example. You can look at high pressure hips, like they call high pressure casting, as well as you can think of casting as investment casting. So there is all these factors that come into play. Sand casting is of course your basic casting. Prepare a sand mold, you pour your metal, the mold gets destroyed, you pull out your finished part. Die casting is very much like injection molding, where you are having a closed cavity, you are pushing metal and forming the parts. So very niche parts, high tolerance, but essentially cheap as well. Then the hips is like, particularly to avoid the voids in the casting, you have a blanket of nitrogen or argon on the cast melt, and then with the force pressure, you are able to close out and collapse those voids and manufacture that way. So you can go anywhere from 50 to 500 psi of pressure. Investment casting is what, like lost wax or lost foam casting, where you prepare a pattern, you basically build a tree with those patterns, right? And then essentially what happens, once you pour your casting, you're slowly driving away the investment. In this case, if it's a wax mold, the wax is going to drive off, that becomes the part. If it's lost foam, you make the foam part like a foam engine, and then as the metal comes into contact with the foam volatilizes, and then the metal takes the shape of the part. So that's why you make complex Honda engines and so on. They're produced through lost foam casting, like lost wax casting there. So now, when you look at a product with cast alone, you have all these things that you can work by itself. Now, in terms of that, when I showed you earlier the way the Granta works, within that you may have now what are the material choices in that, right? If you look at material, I'm going to use aluminum. Within aluminum, I have 20 different alloys that I can work with. So I can really zero down into the specific level of alloy based on knowing what approach is going to shape. The other thing we'll talk later is what should be the shape of it. What are the effects of shape? To get the same part to do the job, but how should I shape it? Should I add a rib here, or should I add a bend here? Should I add a step here? Or should I make it a big monolithic block? All that will dictate my shape factor, which I have not looked at a shape factor here. And then the third thing, of course, is the forgot completely what was the third thing. It'll come to me, yeah. But let's assume that these are factors which we have not yet taken into account Oh yeah, the size, excuse me. So when is casting economical becomes the factor, right? Now castings, in your general knowledge, when would castings be the process of choice over other processes?
Well, if it's extremely complex, if it's very, very large, a lot of times casting is a better way of doing it.
So he captured both those points nicely, complex and large, correct? So when the part is intricate in geometry, has a lot of ribs and a lot of steps and these trusses and intersections, then you want a metal which flows to those areas and fills the gap. But same time, you can't get the level of accuracy like making a watch part in there, like a wristwatch part, right? Because the process just doesn't lend itself to that. You need to go for a micro precision processing to do something like that. So large parts like machine foundations or boat propellers, things which are, or stakes that are buried in the ground. So components which do the function for that scale, but you're not too concerned about very high precision on those parts. In that case, it works. If you are very high precision within the cast family, you probably want to look at die casting, which then gives you a lot of control on the casting. You can get very good wall thicknesses and things like that. So I guess the point I'm trying to drive across is, now as we go down to the processing side, we have to not only know, we did this material index selection and all that, whether the part is processable within the economical scale required for that. The other big thing that becomes a factor is volume. And this I mean is volume in terms of numbers, not in the size volume, right? If you want to make 5 parts, or you want to make 50 parts, or 50,000 or 5 million parts, that's going to change your selection completely, because now a lot of other costs that would factor in start becoming less and less as the volumes go higher and higher. So you have a break-even point for every design, at which point one process starts becoming more economical over the other process. So that is the beauty of scale, I guess, the scale in terms of volume. So that is to be noted here. So on the metal side, we'd like you to, of course I can spend 2-3 days long just talking about each process, but in a very basic sense, forging, like to remember everyone, it's the three-dimensional charge part, which is then deformation process. No volume is gained or lost. You just take a bulk and brute force take it from one shape to the next shape, like crankshafts and connecting rods and railroad ties and things like that. When you look at rolling, like I said, again it's a deformation process, no volume change before, after, same. Now you start with sheets which are a certain thickness and start bringing them to a second thickness in there. Doing so, there's a lot of changes in the microstructure and the material condition which has to be accounted for. Extrusion, like you say, constant die. For the most part, you're pulling the melt from a green state through the die and then shaping it. So I-beams, H-beams, C-channels, profiles, all these kind of complex shapes can be gotten as long as the cross-section remains the same and the material is workable in that type of process. Drawing, of course, all the fine drawing like wires, nails, brads, all the thumbtacks, those kind of wires, etc., become typically the choice of processes is drawing. So extrusion drawing, a lot of similarity. Drawing is typically cylindrical parts or sheet parts. Extrusion is complex shapes in that family. But all these are deformation processes, no volume change, right? When you look at casting, very different family, it's very flow dependent. So the rheology of the metal, the trapped voids in the metal, a lot of impurities that can get trapped in. So all those factors, and then turbulent flow once it enters the die. So when you send it through the risers and the gates, the material in the die has to flow a certain way. And therefore, there's a lot of flow modeling work done in the sense of this viscous flow to make sure that the right entry points in the die are managed. So the material will have very minimal splash and issues that can create voids in the part. So that is a very different type of problems than these. Sheet parts, like we saw, sheets has very close alliance with rolling. because that becomes your first form for getting sheets. And then once you get sheets, you have to work the sheets to usually with a very constant thickness, because every time you draw the sheet on a wall or a bend, you're going to thin the sheet. So how do you manage the thinning versus stretching, right? So there's a competition of strain biaxial stretch in that case. So those are the issues you're working with there. Again, sheet is constant for volume. In this particular case, also it's constant volume, but you're basically adding volume as you go to the from 0 to full part here. So within this, the other thing you have to look at is two more things: is whether it is subtractive manufacturing or is it additive manufacturing. And here additive, I don't mean in the sense of the fancy additives we're getting used to, but additive could simply be welding, adding one layer through welding processes. But subtractive manufacturing means you have to get into metal machining, then your family goes into planing, and then milling, and drilling, and all of the above, right? I don't think lathing is a proper word, but lathe work, drilling, etc., boring, right? All these are machining steps. So you're removing material from that. So most metals have to, at some stage, go through that. Additive manufacturing, like I said, you are doing everything from welding, as well as metals can be SLAs, sintering, you can do powder metal work, you can do fused deposition modeling of metal wires. So there is a whole world out there in terms of adding and building up parts through metal that are good like that. So
would you consider like most composite processing methods additive, in the sense that you're having to like manually put in layers of material?
So there is a subset of families in composites also which are additive certainly, right? Like tape layup would be a common one, or extrusion deposition would be that type of a process.
Which one would injection molding fall into? Is that more of an additive type process?
So injection molding is more like a sand, like a casting process, right? Where you're taking bulk and pellets or bulk material and then filling the part through flow processes. So it's not necessarily additive unless you stretch the definition. So it would be a flow process.
Additive manufacturing would be like electroplating, something like that.
Yeah, not ECM falls under this thing, electrochemical machining, but yeah, electroplating coating could be certainly in that family of things. So here I'm just focusing on the metal family for the time being, but this also starts giving you an impression of how complex this thing can get. It can get complex in a hurry because you have so many choices, and under that so many sub-choices that you work with. So I won't dwell on each of these because that is the subject of a different class, but again, what I'd like for the context of Granta, if you go into any of these and click that, you should be able to get a lot of unstructured information related to that process. I would ask, based on your need, I would invite you to review that type of information, okay? So then, where I'll stop here, but I will continue next class, we'll build up the same processing family for the other materials, and then we will see how Granta then gets used in the process universe. Because so far we have been wandering in the materials universe only of Granta. There is a whole out universe in the process universe which we have to build up upon. And then we tie the materials universe to the processing universe, with cost being the tie rod there, I guess. No pun intended, but that's the next step out there. So we have at least two more classes around this. Shape will be introduced, hybrids will be introduced. And that way I believe we'll have all the necessary tools for attacking anything around this aspect. Any other questions? Except when I will return your graded works. I often ask myself that.
Just like a question go back to like injection molding being subtractive or additive. So what if you consider like when the part comes out with the gates and runners still attached to your individual part, and
Sure.
you have to remove those?
So what is your question?
So like,
there?
you know, like if you make a plastic phone case back,
Yeah, yeah, yeah,
you'll make
sure.
like 40 at once, and it'll all come out, and then the gates and runners will be removed from the actual part.
Correct.
Can you consider that?
Well, that's more of separating the scrap from the blank kind of thing, right? Because then where that comes into play is when we talk of recycling and the reuse of materials. Then that becomes very, very real. Whether it's landfill or does it go back into the process. But in terms of classifying the process, in terms of calculation of material quantity, fill, you got to account for those, right, in your process. But at the same time, whether it becomes used in the downstream, so you can say 80% yield, 20% accounts for all that, what you're saying, right, the gate and the runner systems and everything like that. But they have a lot of value back in the recycling chain, actually.
I think the border gets fuzzy, right? Because there's not a strict breakpoint between additive or subtracting. So a lot of times you classify things like that as simply a finishing operation, and you don't worry about whether your process is additive or subtractive. When you go subtractive after an additive operation, it's usually when you're feeding it into a traditional machining operation, where a lot of parts to establish the final
True, very like cast parts. Once you finish casting, it's very common to surface face not the entire casting, but just the critical flanges or where the gaskets will go in, that kind of thing. So there are elements of each process where some of this appears. It cannot be as cut and dry as this is all subtractive or this is all additive. There's going to be combinations thereof. And like Jared is saying, some of those things, even in machining, all the scrap that gets generated has to have a role in the recycling discussion, which is what we will come back to. And that comes into cost. This metric we have largely avoided yet, but once this comes into play, all those factors will start adding. Cost of scrap and cost of each of the substances. So life is good, but not as easy as it seems. This is what we can say about today. Yes. Okay guys, let's get this test out of the way. Let's start on test 2, and hopefully the modular approach will be more effective. And I must tell you in advance, next week I'm on the West Coast both days, so what I'm thinking is I will record the lectures, and I will, so we will not miss any lectures or anything like that. And I'll take either Alex or Ryan's help to class. So we will take attendance in the class, and I'll be available on phone if you need me to for any questions. I may at least do 1 or 2 days like that. And one day, if you all are okay, I will hand out the first module and you can start working on it. And I'll tell you whether Tuesday I think I'll be in, definitely this is 3 hours behind, so 11 o'clock I know that I'll be in a meeting. And Thursday I'll be on the road somewhere, so I don't want to. So I'll record that over the weekend and keep those ready. And then this Thursday we'll continue with this thought. I think I'll be close to the material industry, the grantor discussion, but I will need at least that one more class to come finish it all. And then I'll feel comfortable assigning work and asking you all to finish the gaps. Okay, thank you, and have a good evening.